Okay, let's work out some examples using spherical coordinates to evaluate various integrals. So the first thing that we're going to do is problem 22. We're wanting to evaluate this integral here, the triple integral of y squared z squared dv, where e is the region above the cone, phi equals pi over 3, and below the sphere, rho equals 1. So before we even really get started with that, let's actually plot that thing. And and while my first instinct might be to go to GeoGebra, it's actually a little bit complicated to actually draw these in GeoGebra unless you know how to use the surface tool. And I haven't really shown you how to do that because that's something we're going to discuss how to do in the next chapter, in fact, um, talking about parameterized surfaces. So let's kind of just think about this and draw by hand. So keep in mind, we are essentially working with our three-dimensional coordinate system. We know what a sphere of radius 1 looks like. So we're going to have some sphere here. I'm not going to draw the whole thing because we're not going to be looking at the entire sphere, but we're going to have some sphere around the origin. The cone phi equals pi over 3. Remember, we're basically looking at all the points that are an angle of pi over 3 from the positive z-axis. So we're starting here and going down by an angle of pi over 3. So you can imagine we're down here. So we have some cone. Remember, phi equals a constant is a cone. So we're going down to some cone. So we have a conical base to it, but then we have part of the sphere at the top. And that is the E that we're looking at. And that actually is a spherical wedge, even though it maybe doesn't look like it. But we're basically saying that our theta value, our rho values are going to go from 0 to 1 because we are allowed to start at the origin and go out to 1. Our theta values, because there's no real limit on that, we can go all the way around the z-axis. Those are going to go from 0 to pi, 0 to 2 pi. And then rho, because we're doing all the stuff above the cone, phi equals pi over 3. We're going to start at 0 at the positive z-axis and go to pi over 3. So 0 to pi over 3. And those are going to just be the limits that we're going to use on our triple integral. We're going to look at the triple integral over e of just y squared z squared dv. We're going to first put our limits for phi, so 0 to pi over 3. Then our limits for theta are 0 to 2 pi, and our limits for rho are 0 to 1. We're going to have to change y squared z squared into rho theta phi. Remember, our formula for y is rho sine phi sine theta. So that thing's going to be squared. Our formula for z is rho cosine phi. That's also going to be squared. Then don't forget the extra factor. We need a rho squared sine phi. That's always going to be there. And then, of course, we have d rho, d theta, d phi. And remember, those have to correspond to the same order. Well, you can say the opposite order if you want to, that we have the limits at the beginning. So 0 to pi over 3 has to correspond to the d phi at the end. Now, most of these problems, because we're not really wanting the actual integration to be the trickiest part here, though we are going to have to deal with some powers of sines and cosines, and those might be a little tricky. But most of them will be things that we can pull apart, especially since we're working with these spherical wedges. So we have stuff in here that's multiplied together that is in terms of rho, stuff that's in terms of theta, stuff that's in terms of phi. Since it's all being multiplied together, I can actually split apart my integral into 3 parts. Basically, I'm going to take all the parts that have a phi in them. That would be a sine here, which is actually squared, so we have sine squared. That's a cosine here, that's also squared, and this extra sine here. So we have 3 copies of sine of phi and 2 copies of cosine of phi. Then I move on to theta. We have 2 copies of sine of theta here. We don't have any other thetas in here, so I just need to integrate sine squared of theta. Finally, the stuff that involves rho, we have 2 copies of rho here, remember that's square, 2 copies of rho here, and then of course always 2 extra copies there. So we actually have 6 copies of rho. And now I need to do all 3 of these integrals. So I'm going to have to move this down to another page. This is not all going to fit on this page. But the first one, so for the rho, or not, for the phi, what I would do here is I would I guess I need to do another step before I do that. What I'm going to do is I'm going to try to make as much of this in terms of cosine as I possibly can. That means I'm going to take my sine cubed and turn that into a sine squared times a sine. The sine squared I can turn into a 1 minus cosine squared. So I have 1 minus cosine squared. I still have this cosine squared. And then I have a copy of sine. And that copy of sine is actually nice because what we're essentially doing here, if you remember back from Calc 2, is we're using the fact that if we have a product of sines and cosines where one of them has an odd power, we basically can pull out one of those from the odd power. That will be part of our substitution eventually. And then everything else, we can use the fact that sine squared plus cosine squared equals 1 to convert that entirely into one trig function. So in this part here, I don't have any sines, and then I have an extra sign over here. Unfortunately, that's not going to work when we're dealing with only even powers, which we do when we have a sine squared. That one we're going to have to actually use the other rule that we use in Calc 2, using the fact that sine squared is actually equal to 1/2 minus 1/2 cosine of 2 theta. Now, of course, the rho part here is actually the easiest part of all of this. We can actually go ahead and integrate that right away. Integral of rho to the 6th power is going to be 1/7 rho to the 7th power, going from 0 to 1. For this first part, the reason why we like to do that is we want to set u equal to cosine of phi. That means that du is negative sine phi d phi. And so that's why we like to have that extra sign there. The sine phi d phi is going to turn into a negative du. Everything here, this is going to turn into a 1 minus u squared times u squared. We'll use the extra negative to actually swap the order of the 1 and the cosine squared, 1 and the u squared. And then I'm going to go ahead and even just expand that all out. But what I'm going to get there is going to be the integral of u to the 4th minus u squared du. The limits, we're going to have to plug in 0 and pi over 3 into cosine. Cosine of 0 is going to give us a 1. Cosine of pi over 3 is actually 1/2. So they're nice to not give us anything that has square roots. Next, we're integrating 1/2 minus 1/2 cosine of 2 theta. Well, the integral of 1/2 is going to be 1/2 theta because we're integrating with respect to theta. The 1/2 cosine of 2 theta, because there's a 2 theta in there, we end up having to divide by an extra 2. So we have a 1/2 times 1/2. And then this the cosine turns into a sine, and that's still going from 0 to 2 pi. And then finally, when we plug in 1 and 0, obviously 0 just gives 0 there, but when we plug in 1, we get a 1/7. So all this is eventually going to be multiplied by 1 over 7. Integrating u to the 4th minus u squared, we get a 1/5 u to the 5th minus 1/3 u to the 3rd. So we're going to go from 1 to 1/2. This one we can go ahead and plug in our values. We have a 1/2 times 2 pi. That's going to give us a pi. Sine of 2 theta, where theta is 2 pi, is going to be sine of 4 pi. But sine of 4 pi is 0. So we're subtracting 0 there. When you plug in 0, this is obviously 0. And sine of 0 is also 0. So we're actually going to take pi minus 3 copies of 0, or just pi. And we still have the 1 over 7, so actually we'll just write that as pi over 7. Finally, we get to plug in our values here. We have 1/5 times 1/2 to the 5th power, or basically we're going to multiply that 5 by 2 to the 5th power. It's 5 times 32, basically. It's going to be a 160. We have 1 over 160. Now we have 1/3 times, well, 1/2 to the 3rd power is 1/8. 1/3 times 1/8 is a 1/24. Now we get to plug in 1 and subtract it. So we're going to be subtracting a 1/5. And because there's a minus sign here already, we're going to be adding 1/3. And then you can go ahead and use a calculator for this part if you want to. Make sure you put it into. We don't want to have decimals here, so we'll make sure you have it as a fraction and not as a decimal. But this whole thing turns into a 47 pi over 3,360. So kind of a complicated looking number there, but it's not as bad as maybe it could have been. We didn't have any roots in there, for one thing. If this had gone from 0 to pi over 6, we would have had a root 3 over 2, and then that root 3 would end up having root 3's in the formula. So maybe not as bad as it could have been, but still maybe not as nice as we would like it to be. But the point here is that all this came down to all Calc 2 stuff eventually. Once we were able to set it up in terms of spherical coordinates, it actually was pretty straightforward to do. But doing this with rectangular coordinates, so with what we were doing before, would have been not very nice at all. We would have had stuff like, we would end up with the top surface here being z equals square root of 1 minus x squared minus y squared, and that would be one of our limits that we'd have to put in. So something like you'd be right here. And then the bottom part, that would be what? I think it'd be like z equals some multiple times the square root of 1 minus x. There would it be? Yeah, I haven't thought that one through, but it would be somewhat similar to that. That would be our other limit for z, would be whatever the formula for that cone is going to be, and that's actually going to be. I guess it wouldn't have the square root. That's what would be the difference. It wouldn't have the square root in it, so that one wouldn't be terrible, but already you can kind of see that things are not very nice already. So that's the advantage of using spherical coordinates. We have this cone, we have this sphere. Both of them are incredibly easy to set up with spherical coordinates, even if we eventually have to do a whole bunch of stuff with integrating sines and cosines. Next problem we're going to do is problem 23. So we're trying to do a triple integral of x squared plus y squared dv, where E lies between the spheres x squared plus y squared plus z squared equals 4 and x squared plus y squared plus z squared equals 9. So we just have two spheres. So one sphere inside the other one. Not very well drawn, but hopefully you get the idea. Our axes are going through the center of those spheres. Now, in polar coordinate, sorry, not polar, spherical coordinates, of course, we're using two radiuses here. We're using 2 and 3. So rho is going from 2 to 3. Theta is going all the way around the circle, so we're going from 0 to 2 pi. And phi, remember, phi varies from 0 at the positive z down to phi equals pi on the negative z. So whenever we're doing anything that involves an entire sphere, those are the limits that you're going to use on theta and phi. And so those are the limits that we're going to have on for our first two limits, for our first two integrals. So phi is going from 0 to pi, theta is going from 0 to 2 pi, rho is going from 2 to 3. We do need to express x squared plus y squared in terms of rho, theta, and phi. But keep in mind, x squared plus y squared, this is the r squared from polar coordinates, from or cylindrical coordinates. And remember, we did have a formula for r in terms of rho and phi. R is equal to rho sine phi. And so that's actually what I'm going to use here. If you want, you could just use the formulas for x and y in terms of rho, theta, and phi, but at that point you'd actually want to, the very first thing you'd want to do is make use of the fact that sine squared of theta plus sine squared sine squared of theta plus cosine squared of theta is equal to 1. And that to simplify the integrand here before you even try to do any integration. But I'm just going to go ahead and use that. Remember, it is going to be squared. So we're going to have rho squared sine squared phi. Don't forget the extra rho squared sine phi. This comes from doing spherical coordinates. It doesn't come from the x squared plus y squared. So those are going to have to be multiplied together. We'd have d rho, d theta, d phi. Of course, we just have a product of stuff here. So I'm going to split this up the same way I did in the last example. I'm actually going to start with theta this time because there are no thetas in our formula here. So the integral from 0 to 2 pi is really just going to end up multiplying this by 2 pi at the end. So that's the contribution of theta. You get a 2 pi factor out inside. Then I'm going to put in the stuff for phi. So we have two copies of sine of phi here. We have a copy of sine of phi here. We're going to be looking at sine cubed of phi, still going from 0 to pi. And then we have, for rho, still going from 2 to 3, we have a rho squared and a rho squared. We have a rho to the 4th. We're going to do kind of the same thing that we did on the last one for the sine cubed. Remember, here we're dealing with again, we're still working with sines times cosines, so we don't really have any cosines here. The idea is that since we have an odd power for one of those, specifically here 3 for sine, we can pull out a copy of sine and then try to convert everything else to cosines. So it might seem weird that we only have sines, now we're trying to introduce cosines, but it does actually help us overall. Essentially, I'm going to pull out a sine. That's going to leave me with a sine squared, which I'm going to convert to a 1 minus cosine squared. And that's going to allow me to make that same substitution that we did before, where u equals cosine of phi, du is negative sine phi d phi. So this will turn into a 1 minus u squared. We'll get an extra minus sign from converting the rest of this to du. So we're just going to turn into u squared minus 1. The row to the fourth, of course, becomes a 1/5 row to the fifth. We're going to have to plug in 2 and 3. And I'm also going to have to do this on another page. So we're going to have that 2 pi with the integral of u squared minus 1 du. Of course, we are going to have to use 0 and pi. Put this into cosine. 0 gives us a cosine of 1. Pi gives us a cosine of -1. When we plug in 3 and 2, we have 3 to the 5th power. 3 to the 5th power is 243. So we'll have a 243 over 5. Then we subtract 2 to the 5th power is 32 over 5. We'll have to simplify that. In fact, let's go ahead and simplify it right now. 243 minus 32 should give us a 211. 211 over 5 times 2 pi. That's going to make this into 422 pi over 5. The integral of u squared minus 1 is going to be 1/3 u cubed minus u. We're going to have to plug in -1 and then subtract what we get when we plug in 1. So plugging in -1, -1 cubed is -1, so we have a -1/3 minus a -1, so plus 1. Then we subtract, plugging in 1 here, so 1/3. And then we subtract a negative, so plus a 1. All this turns into, 4/3. So we end up getting multiply 422 by 4 to get a 1688 pi. And we add a 3 on the bottom, so the 5 becomes a 15. And just like on the previous example, maybe more complicated than we'd like it to be, but it is what it is. I mean, we can't really change the answer there. It just comes straight from what we were trying to do. We were trying to integrate this function over between those two spheres, and that's the answer. Our last problem is going to be problem 26. We want to evaluate this function, the square root of x squared plus y squared plus z squared, where our region is going to be above the cone z equals square root of x squared plus y squared, and we're between the spheres x squared plus y squared plus z squared equals 1 and x squared plus y squared plus z squared equals 4. Now, since they've written all that in terms of x, y, and z, actually I can go ahead and use GeoGebra pretty easily to graph that. So let's start with graphing our spheres. So we have the sphere x squared plus y squared plus z squared equals 1, the sphere of radius 1, and then x squared plus y squared plus z squared equals 4, those in the sphere of radius 4, or no, radius 2. So we're only looking at stuff that's inside there, except we're only concerned with the stuff that's above the cone z equals the square root of x squared plus y squared. And why did it try to do it as an implicit curve? Let me write that as z squared equals x squared plus y squared. It's going to show us as a double cone, but at the very least we can kind of see what's going on here. So we're only looking at the stuff that's between the two spheres that's above this cone, specifically the top cone, because when we wrote it as z equals square root of x squared plus y squared, we were only looking at positive z values. So we're looking at the part that's up in this part of the cone, in between those two spheres. Now, one thing to note here, we do need to convert this into a spherical wedge. Of course, there's no limits on our theta, so theta is definitely going to be between 0 and 2 pi. And it shouldn't be too hard to see that because we're dealing with the spheres with radius 1 and 2, rho is going to be between 1 and 2. Phi is going to be the more complicated one. Obviously, phi being going to 0 for the z-axis, but then how far down are we going to get to this cone? They didn't write that in terms of phi like they did in our first example, so we're going to have to figure out what is that limiting phi. What is the phi that corresponds to this particular cone? Now, I would like to actually write this, well, yeah, let's go ahead and actually write this out. So really, what are we dealing with here? We have z is equal to the square root of x squared plus y squared. Remember, x squared plus y squared is actually r, the r from cylindrical coordinates. Or, well, x squared plus y squared is r squared. When we take the square root, that's when we just get r. Z, remember, z is rho cosine of phi. And r, we already knew, was rho sine phi. That means that cone is where rho cosine of phi is equal to rho sine phi. Of course, the rho's here don't really matter. Those are really just going to be telling us how far out on the cone we are. Going from rho equals 0 at the tip and getting bigger as we go out. Really, it's the angle that's the important thing. And if we go ahead and actually divide everything by cosine, that means sine over cosine, which is just tangent, is going to have to equal 1. What angle, what phi gives us a tangent of 1? That's going to be pi over 4. Sorry, that should be 0. So all this is a long-winded way of saying that this particular cone, z equals the square root of x squared plus y squared, is just the cone phi equals pi over 4. And that's the simplest cone we can actually write down. If we had phi equals pi over 3, the formula we have there would be some multiple of square root of x squared plus y squared. I don't really... we'd have to use some trigonometry to actually figure out what that multiple is. It comes down to the fact that we are kind of working with this kind of a formula here. What multiple here would give us the correct tangent of pi over 3 and all that kind of stuff. I don't really feel like working it out right now. The point is, how do we actually figure out what phi corresponds to a particular cone that they give us? Of course, we're going to have to do this triple integral. So phi is going from 0 to pi over 4. Theta is going from 0 to 2 pi. Rho is going from 1 to 2. The square root of x squared plus y squared plus z squared, hopefully you can recognize that as just being rho itself. We don't have to plug in the formulas for x, y, and z, and then try to use the sine squared plus cosine squared equals 1 formula multiple times to simplify that down. Just recognize that x squared plus y squared plus z squared is just rho squared. Of course, we do have a rho squared sine phi as part of doing spherical coordinates. And then we have d rho, d theta, d phi. So the integrand here is actually not too bad. It is just making sure we could figure out exactly what the limits were from having stuff in terms of x, y, and z, and not in terms of rho, theta, and phi. Because you're usually not going to have them in terms of spherical coordinates right off the bat. You're going to have to figure out exactly what values for rho, theta, and phi correspond to what you're given. Of course, here, because there's no thetas involved inside here, we can actually go ahead and turn the integral from 0 to 2 pi into just a 2 pi on the outside. We're going to go ahead and take out anything that has a phi in it, just because everything's being multiplied together. If this was the sum of rho and sine of phi. We couldn't do that. But most of these examples have been really nice to us. Then we take all the stuff with rho. Rho is going from 1 to 2. And we have rho cubed. This is one where we actually don't have to do as much work to actually evaluate the the phi integral. The integral of sine is just going to be a negative cosine, going from 0 to pi over 4. Integral of rho cubed is just 1/4 rho to the 4th. When we plug in pi over 4, we get root 2 over 2. When we plug in 0, we get 1. I'm going to go ahead and put, because we're subtracting that 1, well, subtracting a negative 1, I'm going to put that 1 in front. 1 minus root 2 over 2. And then here, so you can even go ahead and pull out the 1/4. We have 2 to the 4th power is 16, minus 1 to the 4th power is 1. So we get a 15 here. So we have 15 over 4, we have a 2 pi. I'm actually going to steal the 2 from the 2 pi and use it to simplify this, to make this into a 2 minus square root of 2. But I'm still going to have the 15 over 4, so we're going to have 15 pi over 4 times the quantity 2 minus square root of 2. I think that's the best way of writing that. And there's not really any other simplification we can do. That's going to be our answer here. So hopefully from this you've gotten a good idea of how we actually set these problems up. Again, we're not going to really look at any examples where we're not going to have just constant values for our limits for rho, though that is a possibility. If you want, you can take a look at some of the other problems in this section. I mean, you could even come to my office hours and we could work through one of those kind of problems together. The integral itself, evaluating the integral itself won't actually be too complicated. It's figuring out how to make sure that we set it up correctly. That's really the more difficult part there. I'm going to leave this here, and next class, or next set of videos, we'll look into what all this means in a more general sense, where if we change from rectangular coordinates to any other set of coordinates, how would we handle that in more generality, rather than what we've been doing here, where we actually went and just computed volumes or areas by hand. How can we do that without going through all that work every single time? So, leave this for now. See you there.